Welcome to our online chemistry class. Our topic is transition and inner transition elements. Let us discuss part number 3. So here we have to discuss common properties of D block element. First, physical properties. All D block elements are hard, lustrous and shiny in appearance. They have high tensile strength and they show malleability and ductility. Then in transition metals, N-1D and Ns electrons are nearly same energy and hence they involve strong metallic bonding and have compact structure. Due to this property, they have high density, high melting and boiling points. Due to this, they also exhibit variable oxidation states. Then they are good conductors of electricity and thermal, that means heat. So they are electrically conductors and thermally conductors. Then six properties, they can form alloys with transition and non-transition elements. Seventh properties, many metals and their compounds are paramagnetic in nature. And last property is most of the metals are efficient catalysts. So all these properties, formation of alloy, formation of your magnetism, they are paramagnetic, ferromagnetic, or they are axial catalysts. All these properties that we already discussed in the previous part. So you can revise that once again. Now next one is chemical properties. So all D block elements are electropositive metals, means they donate one or more electron and they form M plus cations. If they donate one electron, M plus. If they donate two electron, M2 plus. If they donate three electron, they form M3 plus. That is electropositive ion. Then they exhibit variable valencies and forms color salt and complexes. So copper, in copper sulfate it shows +2 valency, but copper in Cu2O it forms +1 oxidation state, that is valence, and the color is also different. So copper sulfate is blue in color, okay, ferrous sulfate is green in color, FeCl3 is yellow in color. So and they can also form the complexes, K3FeCN6 potassium ferricyanide, okay, then K4FeCN6 potassium ferrocyanide, and different complexes in which central metal atom mostly is the transition metal. Then they are good reducing agents, so they reduces other substance and they itself undergo oxidation. Then they form insoluble oxides and hydroxides. For example, if you observe the oxide of copper Cu2O, then oxide of iron Fe2O3, these are insoluble in nature, while the hydroxide FeOH thrice, CuOH twice, they are insoluble in nature. Then iron, Fe, cobalt, copper, molybdenum and zinc, they are biologically important metals. Then last chemical properties, they catalyze the biological reaction. So above elements, they catalyze the biological reaction. Now differences, although most property exhibited by these D block elements are similar, and the elements of first row differ from second and third row in stabilization of higher oxidation state in their compounds. For example, molybdenum in its plus 5 oxidation state and tungsten in plus 6 oxidation state in their compounds are more stable than chromium in plus 6 and manganese in plus 7 oxidation state of their compounds. Highest oxidation state for elements of first row is plus 7 for manganese, and in case of third row plus 8 oxidation state as in RuO4 for Ru and OS in OSO4. So this is the difference between first, second and third transition series. Next is the inner transition F block elements, or they are also known as lanthanides and actinides. So they are known as F block element. What is the F block element? The element in which differentiating electrons, that is last electrons, entered in n-2 f orbital. So n-2 is the pre-penultimate shell. So if you observe this diagram, the outermost shell is called as last shell or valence shell. Just before that is last but one, that is penultimate shell, and before to penultimate shell, that is last but two, is pre-penultimate shell. So different colors are shown. So outermost shell is denoted by n, penultimate shell last but one is denoted by n-1, and pre-penultimate shell is denoted by n-2. So if you observe their place, they are placed separately at the bottom of periodic table, main frame of periodic table, in two series. One is for lanthanide, another is for actinides, and they are subset of 6th and 7th period of your main frame of periodic table. Then here is the electron placed in this orbital. So outermost shell contain 2 electrons, then penultimate shell contain 0 or 1 electron, and pre-penultimate shell electrons are from 0 to 40, depends on the number of electrons present in the element in its ground state. Let us discuss one by one. First, properties of a block element. So properties of these F block elements are similar to that of transition or D block elements. Then the electrons are added to n-2 subshell, that is pre-penultimate shell. Then they are placed between n-1d and ns block element. So those elements which are placed after lanthanum, they are called as lanthanides, and those elements which are placed after actinium, they are called as actinoids. So let us discuss first lanthanides. Lanthanides series includes the elements from cerium atomic number 58 to lutetium atomic number 71, with last electrons are added in 4f subshell. This is pre-penultimate shell. Then initially these elements are also known as rare earth elements. They are fairly abundant in earth crust. So the name earth rare earth elements was coined because of the difficulty in extracting them economically in pure form from the other lanthanides having similar chemical property. That's why the name is rare earth element. But nowadays, due to newer separation methods like ion exchange regime, the separation of these elements has become easier and more economical. So nowadays, the rare earth element, this name was not used for lanthanides. Lanthanide is the name. What is the position of the lanthanides in periodic table? Group number 3, period number 6, and after the lanthanide. What is the general electronic configuration? Xenon, atomic number 54. Then electrons are added in 6s orbital because we have to follow the above principle, n plus L rule, then 5d, and then 4f. In this sequence, the electrons will added because n plus L for 6s is 6, for 5d it is 6 is 7, and 4f is 4 plus 3, it is 8. So let us discuss the detailed electronic configuration of lanthanides. You see the next table. Just before that, we will see the properties of lanthanides. First properties, they are soft metals with silvery white color and moderate density is of nearly 7 gram per centimeter cube. Then they are good conductors of heat and electricity. Third properties, except promethium, all other lanthanides are non-radioactive in nature. So promethium is only radioactive. Then the atomic and ionic radii gradually decreases from lanthanum to lutetium, and this property is known as lanthanide contraction. So we will discuss this in detail in our next slide. Then fifth is they react with water and form aqueous solution. Then sixth is the coordination number is greater than 6. We observe that it is in between 8 to 12. So coordination number, the number of ligands surrounded by central metal atom in the coordinate complex. Okay. Then they are strongly paramagnetic. Then the common oxidation state is +3, but they also shows +2 and +4 oxidation state. Then they shows magnetic and optical properties largely independent on environment. These are few properties of lanthanides. Let us see the electronic configuration of lanthanides. First, lanthanum is the element. It is not actually a block element, but their property is similar to lanthanides. So it is studied with lanthanide, but it is actually D block element. Why? See the electronic configuration. It is denoted by La. Then atomic number is 57. So what is our expected electronic configuration? Xenon is the inert gas, atomic number 54. So 3 electrons are added. So out of that 3, 1 electron is added in 5d and 2 electrons are added in 6. So sequence is 6s, 5d and then 4f. So first 2 electrons are added in 6s and the remaining 1 electron is added in 5d. and 4f does not contain electron. So this is the electronic configuration, and same is the observed electronic configuration. As it is not a block element, there is no electron in 4f orbital. So remember this. So then they shows +2 oxidation state. So what is the +2 oxidation state electronic configuration? Here is the correction. Make it correct in your textbook also. So electronic configuration, 2 electrons from 6s are removed. So only 1 electron is remained, that is in 5d orbital. So electronic configuration become 4f0 5d1. Then if that d electron is removed, then it shows +3 oxidation state and the electronic configuration become 4f0. Then atomic radii is 187 and ionic radii is 103. The next element is cerium, denoted by C. Atomic number is 58. So what is our here is the again correction. It is wrongly printed. The observed electronic configuration is written under expected electronic configuration, and expected electronic configuration is written under observed. So exchange this electronic configuration. So what is our expected electronic configuration? So it is the first element from Lanthanides series actually. So xenon 54, then 2 electrons are added. So you have to add 4 more electrons. So 2 electrons are added in 6s and 1 electron is added in 5d and 1 electron is added in 4f. So this is our expectation, because in lanthanum 1 electron is added in 5d. So similarly we can add 1 electron in 5d here and remaining 1 electron is added in 4f. But as it is a block element, the 1 electron is not added in 5d, that electron is also added in 4f. So correct electronic configuration is, or observed electronic configuration is xenon 4f2 6s2. 2 electrons are added in 6s and remaining 2 electrons directly added in 4f. So that is the correct electronic configuration. So make it correct. These are, so change this electronic configuration. So it is the observed electronic configuration of cerium. It is xenon 4f2 6s2. Now if it donate 2 electron from 6s, the 2 electron in 4f are remain. And what is the Ce2 plus electronic configuration? It is xenon 4f2. And if it donate 1 electron from 4f, then it shows Ce3 plus and electronic configuration becomes 4f1. Its atomic radii is 183 and ionic radii is 102. Then next one is praseodymium, denoted by Pr. Then atomic number is 59. So expected and observed electronic configuration is same, xenon 4f3 6s2. Now if it donate 2 electron from 6s, then it shows Pr2 plus and its electronic configuration becomes 4f3. So here is also correction, 4f3. And if it donate 1 electron from 4f3, then it shows Pr3 electronic configuration. So the Pr3 electronic configuration is xenon 4f2. Atomic radii is 182 and ionic radii is 99. Then next is neodymium. The atomic number is 60 and observed and expected electronic configuration is same, xenon 4f4 6s2. Then its atomic radii and ionic radii is 181 and 98.3 respectively. Then promethium, denoted by Pm, atomic number 61. The expected and observed electronic configuration is xenon 4f5 6s2. Then if it donate 2 electrons, then Pm2 plus electronic configuration is xenon 4f5. Here is also correction. Then you can see the atomic radii 181 and ionic radii is 97 picometer. Then samarium denoted by SM, atomic number 62. So here is also correction. You have to write 62 here. The observed and expected electronic configuration is xenon 4f6 6s2. If it denotes 2 electron from 6s, then Sm2 plus, the electronic configuration is 4f6. So write down the correction. And if it donate one more electron, then electronic configuration of Sm3 plus is 4f5. Okay. Then europium, atomic number 63, the electronic configuration is same for observed as well as expected, and it is xenon 4f7 6s2. So this is the stable electronic configuration because 6s is completely filled and 4f is halfly filled. Total capacity of 4f is of 17 electrons. So as 4f contains 7 electrons, so the electronic configuration of EU2 plus is xenon 4f7 and EU3 plus is 4f6. Okay. Then gadolinium GD 64 is the atomic number. Electronic configuration is, so our expectation is xenon, our expectation is xenon 4f8 6s2. So 4f8 means incompletely filled, so one electron from 4f is promoted to 5d orbital. Then the stable electronic configuration is xenon 4f7 5d1 6s2. Now there are 7 electrons, means 4f is halfly filled, which is more stable than 4f8 incompletely filled. So remember this electronic configuration: xenon 4f7 5d1 6s2 for gadolinium. And if it donate 2 electron, the GD2 plus is 4f7 5d1, and if it donate 3 electron, then electronic configuration of GD3 plus is xenon 4f7. Okay. Then terbium, the atomic number 65, the observed and expected electronic configuration is xenon 4f9 6s2. We donate 3 electron, then electronic configuration is xenon 4f8. Then dysprosium dy66 is the atomic number. The observed and expected electronic configuration is xenon 4f10 6s2. And if we donate 3 electron, the electronic configuration is xenon 4f9. Then holmium, the observed and expected electronic configuration is xenon 4f11 6s2. Here again one correction: if we donate 2 electron, HO2 plus is xenon 4f11. Okay. And for HO3 plus it is 4f10. Then erbium denoted by ER, atomic number 68, the observed and expected electronic configuration is xenon 4f12 6s2. When it donates 2 electron, then it is 4f12. Then thulium denoted by Tm 69 is the atomic number. The observed and expected electronic configuration is xenon 4f13 6s2. And if we donate 2 electron from 6s, the electronic configuration is Tm3 plus 2 plus is xenon 4f13. And if it is donate 3 electron, then Tm3 plus is 4f12. Then yttrium denoted by Yb, atomic number 70, the electronic configuration is xenon 4f14 6s2. Same for observed also. If we donate 2 electron from 6s, the Yb2 plus is 4f14. And lastly, lutetium, atomic number 71. The observed and expected electronic configuration is xenon 4f14 5d1 6s2. So if we donate 2 electrons, the electronic configuration is xenon 4f14 5d1, and if we donate 3 electrons, then the electronic configuration is xenon 4f14. So this is about the electronic configuration. Thank you for watching my YouTube channel Mukesh Karma.